Welcome to my channel and lecture series on natural and synthetic materials for refractories. Time is always a big concern for industry personalities, and gaining knowledge in minimum time may facilitate their motivation. Thus, I have tried to compile different alumina resources to make shaped and unshaped refractories. We can start with raw bauxite, which is available in nature and is the mother of any high alumina resources. Concerning resources, certain beneficiation through caustic liquor lowers the concentration of reactive silica and increases the alumina content. Calcined bauxite can be obtained after calcination of raw bauxite, preferably above 1600 degrees centigrade. Some images of both raw and calcined bauxites are given in this slide. Beer's process converts bauxite to pure hydrated alumina, followed by calcined alumina. In brief, wet grinding of the bauxite ore in rod mills, ball mills or semi-autogenous grinding mills produces fine slurry. Digestion of the slurry by caustic soda is being done in vessels under pressure at temperature ranging from 170 to 180 degrees centigrade. It may vary in both sides depending on the type of bauxite being processed. The aluminate solution is then decomposed, producing aluminum hydroxide, which is calcined in a rotary kiln to produce alumina. Here red mud form as byproduct from this process. During this process, seed induces precipitation of aluminum hydroxide. Crystals usually preferred to known as gibbsite. Reactive alumina can be prepared from hydrated alumina, which consists of a smaller crystallite size, is relatively porous and has a higher surface area than calcined alumina. Calcined alumina is used in shaped and unshaped refractories, and preferably it has alpha alumina phase. Based on that rotary kiln processing temperature, the phase can be synchronized. Moreover, tabular alumina and fused alumina both are manufactured through sintering and fusion processes respectively. Sintering and fusion, this is electric furnace, this is below melting point. Some processing videos are shown in the last of this presentation. Gibbsite follows different transformation steps to form and obtain the alpha phase, the desired phase for several shaped and unshaped refractories. This figure provides a brief phase transformation of alumina hydrates in air with respect to temperature, in which enclosed area indicates the range of stability. If we extrapolate this one, open area indicates range of transition. Path B is favored by moisture, alkalinity and relatively coarse particle size, path A by fine crystal size. The sequences may be affected by starting material, heating rates and incorporation of second phase. XRD patterns for different hydroxide and oxide phases may assist in understanding the desired phase for a particular application of interest. So, synchronization of temperature and subsequent characterization XRD, including phase and surface area, it can be done through BT, BET, may assist in picking a particular application. So, suppose if we consider the phase C and G, we can see here C is the gamma phase, G is the alpha phase. So, and at what temperature we can get, we can pick up from this table, and subsequent we can finalize the formation of desired phase. In brief, the processing and properties of the 5 most useful pure alumina have been highlighted here. All can be obtained during or after Bayer's process. Calcined alumina is obtained in the last step of the Bayer's process, which heats the hydrated alumina from the precipitation stage to drive off water and form anhydrous alumina, and process temperature confirms the alumina phase. It may be theta, it may be alpha, depends on your desired phase. Reactive alumina, also known as calcined alumina, is produced by heating aluminum hydroxide, and it has high porous, high surface area and fine crystal size. Tabular alumina crystals are usually produced by heating 20 to 25 millimeter diameter pellets of calcined alumina above 1800 degrees centigrade. It follows sintering, and some literature indicates the preferred temperature is 1925 degrees centigrade, and it is just below the melting temperature of this, and it results alpha alumina phase, large crystal size 40 to 200 micron, hexagonal crystal structure and tablets of crystals. White fused alumina results from the fusion of calcined alumina in an electric furnace, and it also produces the alpha phase. Brown fused alumina is a dense material produced from bauxite raw material. The starting material is bauxite, not the calcined alumina. The end product has relatively high titania, near to 3%, and low iron content, making it particularly valuable in refractory applications. The chemical composition and appearance of different alumina have been shown here. The second slide already demonstrated the image of raw bauxite, and the typical composition of grain of bauxite is given in this table. These are the chemical constituents, typical percentage. These are the chemical constituents, these are the phases. So, that means it can be done through XRF, this one, this phase analysis, these constituents, but this phase analysis we need the XRD. Suitable beneficiation and processing may assist in developing different grades of alumina that are high in purity. Certain allowable impurities in pure alumina are shown in another table. Brown fused alumina has relatively high titania and reflects in color. So, these are some images of calcined alumina directly we can obtain after Bayer's process. This is tabular alumina, white fused alumina, brown fused alumina. So, those processing can be visualized in the next slides. A competitive analysis of tabular alumina and white fused alumina is a hot topic for synthetic material and refractory manufacturers. Tabular alumina has a significantly smaller closed porosity. If we consider these are the grain boundary, so these are the closed with the same magnification, the porosity are smaller in TA compared to WFA. This data has been picked up from this literature. Interestingly, it has less open porosity, 1.5 in case of tabular, in case of white 5.5, as well as mean pore diameter is also less compared to WFA. The closed porosity of sintered high alumina aggregates is also the reason for their good thermal shock resistance compared to fused alumina. Pores prevent the propagation of cracks that have been generated by the thermomechanical stress induced by the thermal shock. It is believed to improve toughness by arresting cracks. If crack is propagated, and it can arrest by this, but if crack is propagated, it will propagate direct. There is very less chance of the arresting. The percentage of undamaged grains of tabular alumina after 20 thermal shock cycles is 4 to 5 times higher for fused aggregates with comparable chemical composition. In a recent literature illustrates the calculated infiltration speed of a pore with a size of 50 micron. Here we can see this is the range of 30 to 40 in case of W. These are the sizes. By a typical steel slag is more than 100 times higher than for a pore of 1 micron. Here is near to 4 micron. So, it is quite obvious the degree and rate of corrosion of WFA is more compared to TA. Despite such advantages, high crystal size may exhibit high corrosion resistance. A couple of videos represent the manufacturing processes of tabular alumina and fused alumina. Another you can references and you can follow them. After getting the deductions of the fused alumina from the calcined and diamond are required to modify This is the video for WFA. Relevant references has been given and more details can be found here. I hope you enjoyed the lecture. Thank you for being so patient.